Assalamu alaikum. It's Ahlam Deep, and I'll be explaining Chapter 2, Rate of Reactions, Part 2. Before we start, please prepare your stuff. At the end of this video, you will acquire these objectives. You already know from the previous video that we can represent the variation of the concentration or number of mole of a reactant or that of a product. For a reactant, we will obtain a descending curve, while for a product, we will obtain an ascending one. These two curves are called kinetic curves. Also, if we want to determine the average rate of a reaction, we may refer to the average rate of disappearance of reactant or the average rate of formation of a product, while to determine the instantaneous rate of a reaction, we may refer to the instantaneous rate of disappearance of a reactant or the instantaneous rate of formation of a product. You also know from previous grades, if we want to calculate the speed of the car, we have to divide the distance covered over the time taken to cover this distance. Similarly, the rate of a reaction is the change in concentration or number of mole of reactant or product per unit time. So, if the rate is equal to the change in concentration of S over the change in time, we can write it by delta concentration of S over delta T. S in this case will be the reactant or the product that we are talking about. These two brackets mean the concentration of S in mole per liter, and the time can be expressed in seconds, minutes, or hour. So the unit of rate in this case will be the unit of concentration over the unit of time, which can be mole liter minus 1, second minus 1, or mole liter minus 1, minute minus 1, or mole liter minus 1, hour minus 1. If the rate is equal to delta N over delta T, the change in the number of mole of S over the change in time, in this case, N is the number of mole of S in mole. The time can have these different units, and the units of rate in this case will be the unit of the number of mole over the unit of time, which can be mole second minus 1, or mole minute minus 1, or mole hour minus 1. Let's go back to the reaction of video 1, where a reactant A produces a product B. These are the kinetic curves of A and B. To determine the average rate of formation of B, we have to express it by rate R, the letter R, this dash for average. So this is the average rate of formation of B, since it is a product, between the instant 150-300 seconds is equal to delta concentration of B over delta T, equal to the concentration of B at T equal 300 minus the concentration of B at T equal 150 over T2 minus T1, equal to T2 is 300 minus T1 150. The concentration of B at T equal 300 second is known from the graph. So for T equal 300, the concentration of B is equal to 1.5 mole per liter. So we write here 1.5 minus the concentration of B at T equal 150 will be equal to 1.1 equal to 0.00266. Try to write the number in scientific notation as 2.66 times 10 to the power minus 3, and the unit will be the unit of the concentration over the unit of time. So mol, liter minus 1, second minus 1. So please, each time you determine the rate, don't forget to mention the unit. If we join these 2 points drawn on the graph together, we will obtain a straight line that cuts the curve in 2 points B1 and B2, and the average rate of formation of B will be equal to the slope of this secant, which is the difference of the ordinates of these 2 points over the difference in their abscissas. So the average rate of formation of B, which is a product, within the interval of time, delta t, is equal to the slope of the secant to the curve, concentration of B equal f of t at the points of abscissa T1 and T2. For the same reaction, A produces B. To determine the average rate of disappearance of A, which is a reactant, we will write it as follows. R, the average rate of disappearance of A within the interval of time 150-300 seconds, is equal to delta concentration of A over delta T equal to concentration of A at 300 seconds minus the concentration of A at T equal 150 seconds over T2 minus T1 equals to 300 seconds minus 150. For the concentration of A at T equal 300, let's see the graph. So for T equal 300, okay, this is the kinetic curve of A. The concentration of A is equal to 0.2 mol per liter minus for T equal 150, the concentration of A is equal to 0.6. Pay attention here that 0.2 minus 0.6 will give us minus 0.4, so the value here is negative. We have to put here a negative sign, a minus, and also here to get a positive value for the rate. So the average rate of disappearance of a reactant is always equal to minus delta concentration of the reactant over delta T. Since delta, the difference in the concentration of a reactant, is always negative, with the minus put here, we will get a positive value for the rate. And the answer will be 0.00266 equals to 2.66 times 10 to the power minus 3. The unit is mol, liter minus 1, second minus 1. Also, if we join these 2 points together by a straight line, we will get a secant that cuts the curve in 2 points, A1 and A2, and the average rate of disappearance of A will be equal to the negative slope of the secant equal to the difference in the ordinate of these 2 points over the difference in their abscissas. So, as a result, the average rate of disappearance of A, which is a reactant, within the interval of time delta T chosen here, is equal to the negative slope of the secant to the curve, concentration of A, the reactant, equal F of T at the points of abscissas T1 and T2. Now, what about the average rate of the reaction? The average rate of the reaction in this interval of time 150-300 seconds is equal to the average rate of formation of B within the same interval of time, or it's equal to the average rate of disappearance of A in the same interval of time, equal to 2.66 times 10 to the power minus 3 mol, liter minus 1, second minus 1. What if the stoichiometric coefficients of the reactants and the product aren't equal to 1? What happens to the average rate of the reaction? Let's see. For this reaction, N2 plus 3H2 gives 2NH3. We have this reaction, and we have a table for this reaction. We have an initial mixture made up of 10 mole of N2 and 40 mole of H2. The number of mole of the product at T0 is equal to 0. Pay attention that the mixture of reactants here, 10 and 40, isn't stoichiometric, since 10 and 40 aren't proportional to 1 and 3, the stoichiometric coefficients of N2 and H2. So at T final here, N2 will be totally consumed. We will have a value of 0, while H2 we will have an excess and a certain number will remain here. The evolution for this reaction is minus x for N2, minus 3x for H2, and plus 2x for NH3. At T equal 5 minutes, we have 5 mole of N2. This means that 5 mole remains. This means that the number of mole of N2 reacted is 10 minus 5 is equal to 5. So x is equal to 5. To find out the number of mole of H2 that remains at T equal 5 minutes, we are going to make the difference n of H2 that remains at T equal 5 minutes is equal to n of H2 initial minus n of H2 reacted. It is 40 minus 3x. X is equal to 5, so we will get 25 mole. To determine the number of mole of NH3 formed at T equal 5, we have to calculate 2x. 2 times 5 equal 10 mole. At T equal 15 minutes, the number of mole of N2 is 2 mole, and at T equal 1 minute, the number of mole of N2 is 1 mole. Please take 2 minutes to solve and to fill the table with these values. Your answers should be as follows. Now, for T final, the end of the reaction, N2 will be totally consumed since the ratio of N2 is smaller than that of H2. Or by simple looking to these two numbers, we see that they aren't proportional to 1 and 3 as we've said before. So this N2 will be consumed totally and the number of mole of N2 will be equal to 0. So X, the number of mole reacted, is equal to 10 and the number of mole of N2 remaining is 0. That for H2 is 40 minus 3x. For x equal 10, we will get 10 mole, and the number of mole of NH3 produced at the end of the reaction, which is the maximum value reached, is equal to 2 times 10 equal to 20 mole. We will use this table to determine the average rate of disappearance of H2 within the interval of time 5 minutes, 15 minutes. First, H2 is a reactant, so the average rate of disappearance of H2 in the interval of time 15 minutes is equal to minus delta N of H2 over delta T. Minus, since H2 is a reactant, so delta N will be negative. To have a positive value for the rate, we put minus here. Okay, so it's equal to minus number of mole of H2 at T equal 15, which is equal to 16, minus the number of mole of H2 at T equal 5, which is 25, over T2 minus T1 is equal to, as we've said, 16 minus 25 over T2 minus T1, which are 15 minus 5. 16 minus 25 gives a negative value, minus 9. And with the minus here, we will get 9 over 10 equals 0.9. Don't forget the unit is the unit of N over the unit of T, so it is mole minute minus 1. Let's now determine the average rate of disappearance of N2 within the interval of time 5 minutes, 15 minutes. Take 2 minutes and solve this part. So the average rate of N2 in the interval of time 15 is equal to minus delta N of N2 over delta T, since N2 is a reactant, is equal to number of mole of N2 at T equal 15, which is 2 mole, minus the number of mole of N2 at T equal 5, which is 5 mole, over 15 minus 5. 2 minus 5 equals minus 3. With the minus here, we will get 3 over 10 is equal 0.3, and the unit is mole minute minus 1. These two numbers are different. So, once more, the average rate of disappearance of H2 in the interval of time 5:15 is equal to 0.9 mol minute minus 1. That of N2 is equal to 0.3 mol minute minus 1, calculated before. Now, let's determine the average rate of formation of NH3 within the interval of time 5:15 minutes. Please take 2 minutes and solve this part. The average rate of formation of NH3 in the interval of time 5:15 is equal to delta N of NH3 over delta T. We don't put a minus here since NH3 is a product and the value of delta N is positive, is equal to number of mole of NH3 at T equal 15 minus number of mole of NH3 at T equal 5 over T2 minus T1 equals to 16 minus 10 over 15 minus 5. 16 minus 10 is equal to 6 over 10 equals 0.6 mol minute minus 1. The three values of rate are different. What if we want to calculate the average rate of the reaction in this interval of time? Observe the stoichiometric coefficients of the reactants and the product and compare them with the values of rates calculated before. Yes, we notice that the average rate of disappearance of N2 in the interval of time 5:15 is equal to 1 over 3 the average rate of disappearance of H2 in the same interval of time. Also, the average rate of N2 in the same interval of time is equal to 1 over 2 the average rate of formation of NH3 within the same interval of time. So the average rate of the reaction in this interval of time will be equal to either the average rate of disappearance of N2 or 1 over 3 the average rate of disappearance of H2 or 1 over 2 the average rate of formation of NH3, which are equals to 0.3 mol minute minus 1. So, for the reaction in which the reactants and the products have stoichiometric coefficients different than 1, and during an interval of time delta T, the average rate of the reaction is equal to the average rate of disappearance of reactant A over the stoichiometric coefficient A, equal to the average rate of disappearance of reactant B over the stoichiometric coefficient of B, which is small b, is equal to the average rate of formation of C over the stoichiometric coefficient C is equal to the same for the product D. So also we can say that the average rate of the reaction is equal to, if we replace the average rate of disappearance of A by its value, we will get minus delta A over delta T, and this is the stoichiometric coefficient A remains here, equal to the same for B, equals to 1 over C, delta concentration of C over delta T, and the same for D. Remember that these two minus here is because the reactants are decreasing with time. So delta concentration of the reactant will have a negative value, and with the minus here we will get a positive value for the rate. Okay, while this is not a problem for the product, since the number of mole or the variation of the concentration of the product increases with time. So always remember that the rate of a reaction has a positive value, and when we are going to determine the average rate of a reaction, we must use the stoichiometric coefficients of the reactants and the product. Now, let's do an application, number 2 of the sheet. Please take 3 minutes, read the number and try to solve it. Now, pay attention here that delta N of O2, which is a reactant, is equal to minus 5 mol, minus, since the variation of the number of mole of the reactant is always negative, since N2 is smaller than N1. So if you want to calculate the variation of the number of mole of NO, which is also a reactant, if we are going to refer to the stoichiometric coefficients of the reactants and the product, we say that N of NO over 2 is equal to N of O2 reacted over 1 is equal to N of NO2 produced over 2. If we are going to use delta, so we are going to put minus delta N of NO over 2 is equal to minus delta N of O2 over 1 equal delta N of NO2 over 2. The 2 minus here is, since delta N of NO and that of O2 are negative, with the minus here we will get a positive value which will be equal to that of NO2, which is a product. So the delta N of NO taken with O2 will give us that delta N of NO will be equal to 2 times delta N of O2 equal 2 times delta N of O2 is equal to minus 5. So the variation of the number of mole is equal to minus 10. For delta N of NO2, delta N of NO2 will be equal to 2 times minus delta N of O2. This is the minus, and because delta N of O2 is minus, so we'll get 10 mole, which is the variation of the number of mole of a product which will have a positive value. Now, part B of the question, please read it very well and take 2 minutes to solve it. Now, to calculate the average rate of disappearance of O2, we are going to write the formula. Average rate of disappearance of O2 is equal to minus delta N of O2 over delta T, minus, since O2 is a reactant, so minus 5 mole over 100, we will get 0.05 mole second minus 1. And the average rate of disappearance of NO will be equal to 2 times that of O2 is equal to 0.1 mole second minus 1. Now, for the part C, please take 1 minute and solve it. Also, the answer here is the average rate of the reaction is equal to the average rate of disappearance of NO over 2 equal to average rate of disappearance of O2 over 1 is equal to average rate of formation of NO2 over 2. We will take these two together to say that the average rate of the reaction is equal to that of O2 is equal to 0.05 mole second minus 1. We came to the end of our video for today. This is the summary that you have to write on your chemistry copybook, and this is your agenda. See you soon in the next video. Wassalamu alaikum.